You ever stop and think about that? How does the sound of, say, a guitar get from the real world, from a physical vibration, all the way into your phone? It's an incredible journey from something real to a bunch of code. And today, we're going to pull back the curtain on the secret life of digital sound.
Okay, but before we get into the nitty-gritty, let me ask you something. You know those epic Hollywood space battles, right? A massive starship blows up and you get this huge booming explosion? Well, here's the thing. In reality, those battles would be completely silent. So why? The answer to that question is the key to understanding what sound is in the first place. It's because sound isn't really a thing. It's more of an event. It's a physical pressure wave. I mean, it's literally molecules bumping into each other, and it absolutely needs something, a medium, to travel through. The classic example is ripples in a pond. You can't have ripples without the water, right? Well, in the vacuum of space, there's no air, no water, nothing for those vibrations to travel through. No medium, no sound. Just silence. No epic kaboo. Okay, so if sound is this physical wave moving through the air, how in the world do we get that into a computer? We have to somehow capture it, and that brings us to a really big problem. How do you translate the language of our world, which is smooth and analog, into the language of computers, which is all about ones and zeros? So here's the core of the issue. A real-world sound wave, an analog wave, is perfectly smooth. It's continuous. That means between any 2 points on that curve, you can always find another point, and another, and another. There's literally an infinite amount of detail packed in there. So how can a computer, which can only deal with finite bits of information, possibly store something infinite? It seems impossible, right? Well, the solution is actually pretty genius. It's a process called sampling. The idea is, instead of trying to capture that entire infinite wave, we just don't. We take thousands of tiny little snapshots of the wave's position every single second. You know, it's kind of like how a flip book works. You have a bunch of still images, but when you flip through them fast enough, it looks like smooth motion. We're doing the same thing here, creating the illusion of a smooth sound wave from a whole bunch of tiny digital measurements. So here's how it breaks down. You start with that original, beautiful, smooth analog wave. Then the computer comes in and takes a measurement, a sample, at a very specific point in time. Then another, and another at perfectly regular intervals. Then it just connects the dots. And what you end up with is this, well, it's a stepped, kind of blocky version of the original. It's not a perfect one-to-one copy, for sure, but if you take enough samples, it gets so close that our ears can't tell the difference. Right, so just how close that digital copy gets to the real thing, that depends on a couple of really important factors. And this leads us to the big fundamental trade-off that pretty much everyone who works with digital audio has to struggle with. It's this constant battle, quality versus size. Think of it like you've got two main dials you can turn to adjust the quality. The first one is the sampling rate. That's all about how often we take a snapshot. It's measured in hertz. The more snapshots you take per second, the more accurate your final picture of the wave is going to be. Simple enough? The second dial is bit depth. This one's about how much detail you're packing into each one of those snapshots. A higher bit depth gives you more dynamic range, which is just the difference between the absolute quietest sound and the absolute loudest sound you can capture. And these technical terms, they actually translate directly to things you've definitely heard of. So CD quality audio, the gold standard for a long time, that uses a sampling rate of 44,100 times per second and a 16-bit depth. Now compare that to something like, say, old school radio quality. You're looking at a much, much lower sampling rate and only half the bit depth. And believe me, you can absolutely hear the difference between the two. And this is where that quality versus size trade-off really hits home. Just look at this. For only 10 seconds of audio, CD quality takes up 1.76 megabytes. Now watch what happens. If you cut the sampling rate in half, boom, the file size gets cut in half. Then if you cut the bit depth in half, boom, it gets cut in half again. It's this constant balancing act. Do you want that perfect, pristine quality? It's going to cost you in storage space. Yeah. Think about that, 1.76 megs for just 10 seconds of sound. Now imagine a whole 3-minute song or a 2-hour movie. The amount of data just explodes. It adds up so fast. So, the big takeaway here is pretty clear. When we're talking about digital audio, we're talking about making a recording. And the higher the quality of that recording, the more data it's going to eat up. But what if there was a completely different approach? A way to create sound that didn't involve recording the actual sound wave at all? And that brings us to a totally different philosophy, a whole new way of thinking about sound on a computer. We're moving away from recording and into the world of instruction. This is the big comparison, digital audio versus MIDI. Okay, I want you to think of it like this, because this is the best analogy I've ever heard. Everything we've discussed up to now, digital audio, is like a photograph of sound. It's a perfect, detailed snapshot of a sound at a specific moment. MIDI, on the other hand, is a recipe for sound. It's not the final cake. It's just the list of instructions. Add flour, add sugar, bake at 350. It tells a computer how to make the sound.
So, MIDI stands for Musical Instrument Digital Interface, but what it is basically digital sheet music. A MIDI file is super small because it's just a text file with instructions. It's saying, hey, computer, play a C sharp, use a piano sound, play it this loud, and hold it for 1 second. That's it. It is pure information. There is literally zero sound recorded in that file.
And this is where the difference becomes really important. Digital audio is a recording, right? So its quality is baked in. It's device independent. A high-quality recording will sound great on anything you play it on. But MIDI, since it's just a recipe, it is completely device-dependent. The final sound totally depends on the quality of the cook, or in this case, the instrument that's playing it back. You can have a brilliant recipe, but if you give it to a cheap, tinny-sounding keyboard, you're going to get cheap, tinny-sounding music. And of course, you can't write a recipe for the human voice, so MIDI is useless for spoken dialogue. All right, so we've got these two totally different ways of making sound happen on a computer. The recording and the recipe. The photograph and the instructions. So let's put it all together and see how this actually shows up in the stuff we listen to and watch every single day. Yeah, just think about a movie. When we say sound, we mean everything. The dialogue, the big sound effects, the music swelling in the background. And to create that entire soundscape, filmmakers are using both of these toolkits we've been talking about. And once you know what to listen for, you'll notice these two paths everywhere. The words an actor speaks in a movie, that has to be digital audio. It's a recording of their actual voice. But what about the music in a video game that suddenly gets more intense when you start a fight? That's very often MIDI. It's a recipe the game engine can change in real time based on what you're doing. And your favorite song or podcast on your phone. That's digital audio too, just a compressed version to save space. And just to add one last little piece to the puzzle, let's talk about packaging. You've heard of MP3s, right? Well, the MP3 part is the codec. That's the language or the method used to shrink the audio file down. And the file name you actually see, like .wav or .mp4, that's just the container. Think of it like the box that all the sound data gets shipped in. So you see, digital sound isn't just one single thing. It's a whole toolbox. And the real key is just understanding the difference between capturing a moment in time, the recording, and writing a set of instructions, the recipe. So here's my challenge to you. The next time you're listening to a soundtrack or playing a game, really listen and ask yourself, am I hearing a photograph or am I hearing a recipe?